Hi, can you hear me? Hello.
Hello?
Yeah, can you hear me?
Yeah, I can hear you.
Right. Okay. So today we'll continue with number theory, and I want to look at some of the problems in theory that is related to divisibility and congruences. Okay.
Okay.
So so far what we have learned is that if a and b are integers, we say that B divides A, and the way we write it is this notation: B divides A. If there is some integer C such that A is equal to BC, right?
Yeah.
So this notation means B divides A, or we can also say that A is divisible by B. And the
Yes.
condition is that A is equal to BC, where C is some integer, right?
Right.
Now, some of the basic properties that are a consequence of this is that since A is equal to A into 1 or minus A into minus 1, from here we see that 1 divides A and minus 1 divides A for any A. So basically 1 and minus 1 will divide every integer, right?
Yeah.
Because you can write any integer as a product of another integer and 1 or another integer and minus 1, right?
Yes.
Similarly, you can say that any integer divides 0. Any integer divides 0 because you can say A divides 0 because always A 0 is equal to A times 0, right?
Yeah.
Because this is the definition for saying that B divides A. So you can always say 0 is equal to A times 0. So A divides 0, right?
Yes.
Then the third consequence is the only divisors of 1 are plus 1 and minus 1. That is obvious. Again, the only divisors of 1 are plus 1 and minus 1. Then one second. Then we come to the definition of remainder. So we say A mod B. A mod B, what this means is remainder when A is divided by B. When A is divided by B, right? The next consequence here is if A belonging to integer is divisible by B belonging to integers, then either of A and minus A is divisible by either B or minus B. All of this follows from the definition directly, right? I hope you are understanding that this
Yes.
is all from the definition of A divides B.
Yes.
Another consequence is if AI and BI, where one is less than equal to I less than equal to N, are integers such that BI divides AI, then B1, B2 till Bn will divide A1, A2 till An. The product of the divisors will be dividing the product of the dividends, right?
Yeah.
Hmm. Now, uh, one thing to remember in divisibility problems, if we need to prove in number theory that A is equal to B, two numbers are equal. One way to prove it is that A divides B and B divides A.
Yes.
Show this. If you can show that they divide each other, then they have to be equal to each other, right?
Yes.
Okay, so let's look at a few questions to just apply all of this. So, question one is let A greater than equal to 2 and M greater than equal to 0, N greater than equal to 0 be integers. Prove that one of A power M and A power N divides the other. Use the definition to prove it. Don't try anything else, just the definition.
For the first one, wouldn't it just be like, you could say that AM over AN is equal to AM minus N, and that proves it divides the other?
You have to use the definition to show it. So something divides the other. You have to show that the other one should be the product of that first thing and some other integer, right?
Right. So,
You can assume without loss of any generality that one of them is bigger than the other. M is greater than N or something. Case
so
one.
can so can you just say that, like, suppose N is greater than M, so you could just say that AM times AN minus M is going to be equal to AN?
Hmm. So basically, both of them are integers now. A power M is there, and another integer A power N minus M is there.
Yeah.
And product of these two integers is equal to the A power N. Therefore, A power M divides A power N. And similarly, you can prove in other cases also from the definition.
Right.
Try the other one.
Okay.
You should recall that 441 is what? 21 square.
Yeah, so then because it's 21 squared, it's going to be 3 squared times 7 squared is
Hmm.
441. So then you get,
Something like
you
this,
can,
right?
yeah,
And then you can easily show that this number is a product of this and another integer.
yeah, yeah.
So it's over. Then third problem is prove that n into n plus 1 is divisible by 2 for any n. And fourth one is prove that n into n plus 1 into n plus 2 is divisible by 6 for any n. These are quite easy. You should easily be able to say this.
Is it because like they're consecutive digits, so one always has to be even, and then even times an odd is a,
Mhm. So one of them is going to be even, so one of them is divisible
yeah,
by 2.
yeah.
Okay. Fourth one,
Okay. Isn't this one like the same thing? N times n plus 1 is going to be divisible by 2 because it's an even number. And then because there's like 3 of them, at least one of them is going to be a multiple of 3. So
hmm,
then the entire thing should be divisible by 6.
right? Any product of any three consecutive numbers will be divisible by 3.
Yeah.
So in general, what you can say is that the product n, n plus 1, n plus 2 goes on till n plus m minus 1 basically is the product of m consecutive integers, right?
Yeah.
This is going to be divisible by m, right?
Yes.
This is divisible by m. Why is it divisible by m? What is the general reason we can give? Basically, we have to look at these m integers, right? These are my
Yeah.
integers, and you can go till here and think of all of these integers modulo m, right?
Yes.
Now, when you do modulo m of anything, the remainders can be anything from 0 to m minus 1, right?
Right. Yeah.
These are the possible remainders, right?
Right.
So obviously, it can't be just leaving remainder 1 to m minus 1. That is only m minus 1 of them, right?
Yeah.
One of them has to be having remainder 0
Right.
because there are m of them and these are m remainders, right?
Correct.
So if one of them is remainder 0, then that means that one is divisible by m.
Yes.
And then the whole product will be divisible by m, right?
Right.
So that is a general thing that will be useful in problems. Okay.
Okay.
Uh, Fifth one is this. Prove that for all odd integers, n, we have 8 divides n square minus 1. Fifth one, have you gotten something? Anything?
I just said like, let's say we have this number k, so then 8k plus 1 is going to be equal to n squared.
No,
And
we
then
have to
8k,
show that. No, you can't
yeah,
assume it. Why are you trying to assume it? For all odd integers, you have to prove that 8 divides this. You cannot say that, yes, let's say n square minus 1 is equal to 8.
right.
You're
So,
assuming what you have to prove.
I mean, wait.
That's the final step that proves that, yes, it is divisible by 8. You cannot start from there. You understand what I'm saying?
Yes, I understand. So, since n is an odd number, you could say that n is like some k plus 1.
What k plus
So,
1?
like, and because it's odd, you could just write it some k plus 1 to show
No,
that it's a number.
no, we can't. N cannot be written as k plus
Oh,
1.
sorry,
K,
2k plus 1, 2k plus 1.
please don't say such things. You need to know how to write odd and even numbers by now.
Yeah. And then 2k plus 1 is basically 4k squared plus 4k plus 1. And then you subtract 1, so it's 4k squared plus 4k. And you can take 4k common to get 4k times k plus 1. And then, so you have a 4. And then,
We have already done a question which will help you prove this last step. What would you learn in question number 3?
In question number 3, oh, consecutive digits, 1 is always divisible by 2. So then 4 times k plus 1. So k times k plus 1 is going to be divisible by 2. And then 4 times 2 is 8. So it's divisible by 8.
We know that k times k plus 1 will be an even number, so it will be something like 2m or something.
Yeah.
And you will say 4k into 2m is equal to 8 into k into m. Clearly, 8 is dividing it.
Right.
Question number 6.
Okay.
Don't try to put 2k plus 1 directly first. First, you should try to factorize it.
Yeah.
Here also n is odd. You can think of 2k plus 1 later, but first factorize the expression. This much should be obvious.
Yeah.
What can we write about n power 8 minus 1?
You could say it's n4 minus 1 plus times n4 plus 1.
So what can we say about n power 4 minus 1? That can be further factorized, right?
Yeah, into n squared plus 1, n squared minus 1.
So we have basically n square minus 1 whole square, then n square plus 1 whole square,
Yeah,
and n power 4 plus 1.
right.
We have to prove that 512 divides this whole thing. 512 is, by the way, 64 into 8. So it is 8 cube.
Yeah.
Using the previous problem, we already know this, right?
Right.
So obviously we know that 8 square will divide this much.
Yes.
You already know 64 will divide n square minus 1 whole square.
Yeah.
Can you prove that there is another 8 that divides this? That's what you have to prove, right?
Right. Yeah.
If you can get another 8, then the whole thing is divisible by 8 cubed. Now you should think of the fact that n is odd.
Yeah, and plug in 2k plus 1.
N is odd, then obviously n plus 1 is even.
Yeah.
So actually it's not n plus 1, it is n square plus 1. So, but still that is also even because n square will be odd, so n square plus 1 will be even, right?
Yeah.
So if this is an even number, when you square it, it will be divisible by 4.
Yes.
Divisible by 4. And obviously, similarly, n power 4 is odd. So n power 4 plus 1 is even.
Yes.
So there will be another divisibility by 2 coming from here, right?
Yes.
So overall, the product will be divisible by 4 into 2, 8.
Correct. Yeah.
Do you understand what we are saying?
Yes, I understand.
We already know 8 divides n square minus 1. That we already did. For
Yeah.
n being odd, not in any other case. And we got 8 square from there. And another 8 we are getting where because n square plus 1 and n power 4 plus 1 are both even.
Yeah.
Okay. Let a and n greater than equal to 0 be integers. Prove that a square plus a plus 1 divides a power 2 power n plus 1 plus a power 2 power n plus 1.
Oh,
So this is a case, this works out because of a set of identities. First of all, you need to see when n is 0, n is 1, what does this look like? N is 0, what is this looking like? A power 2 power 1 plus a power 2 power 0 plus 1, right?
yeah.
So that is what? A square plus a plus 1, right?
Yeah.
Obviously, a square plus a plus 1 will divide a square plus a plus 1. This is the case
Right.
n is 0, n is equal to 1. It is a power 2 power 2 plus a power 2 power 1 plus 1, which is like a power 4 plus a square plus 1.
Yes.
As you keep increasing the n, you are getting a power 2 power 3, so a power 8 plus a power 2 power 2, so a power 4 plus 1. Terms like this, right?
Yeah.
We need to show that in general, a square plus a plus 1 will divide any such term, this or higher terms also,
Yeah.
right? So what you need to think of is, can we write an identity where we can prove that a square plus a plus 1 divides this? So you can actually see that, because find out what is a square plus a plus 1 multiplied by a square minus a plus 1. That is clearly going to be equal to a square plus 1 whole square minus a square. That is equal to a power 4 plus 2a square minus a square. So plus a square plus 1, right?
Yeah.
So when you multiply these two, you are getting this.
Right.
Similarly, when you multiply a power 4 plus a square plus 1 and multiply it with a power 4 minus a square plus 1, you will end up getting a power 8 plus a power 4 plus 1. You have just replaced a with a square here everywhere.
Yeah.
So basically, you have identities like these, which are always a square minus b square identity we are using to get all of it. So if you have a
Right.
square plus a plus 1, multiply it with a square minus a plus 1, you will get a power 4 plus a square plus 1. And
Yeah.
in this first one, we have replaced a with a square everywhere,
Right.
right?
Yeah.
Then you replace a with a power 4 also you can do, and you'll get a with a power 4. You'll get a power 8 plus a power 4 plus 1, a power 8 minus a power 4 plus 1, and a power 16 plus a power 8 plus 1, right?
Yeah.
We can keep making, we can keep replacing a with a square, a power 4, a power 8, a power 16, or powers of 2, and you will keep getting different identities like this, right?
Right.
So ultimately, the last one will be replace a with a power 2 power n,
Yeah.
right? So in that case, you will get the last one. Let's write the last term, a with a power 2 power n, but square of that. So it is a power 2 power n plus 1 plus a power 2 power n plus 1, right?
Right.
A power 2 power n plus 1 minus a power 2 power n plus 1 will be equal to, this side it will be a power 2 power n to the power 4, so 2 power 2, so a power 2 power n plus 2 plus a power 2 power n plus 1 plus 1, right?
Yeah.
This is that last identity if you keep doing this replacement. Now, if you take each of these equations and multiply it out, left hand side and right hand side, just multiply, you will see that when you do the product, finally many things will cancel. For example, this is canceling with this is canceling with this, right?
Right.
So what you will end up with is this series of things. This term will cancel from the previous one, right?
Right.
So you will end up with a series where something like this you can show that a square plus a plus 1 times a square minus a plus 1 times a power 4 minus a square plus 1. All the second terms are still there. No? The first terms got cancelled.
Yeah.
This product till a power 2 power n minus a power 2 power n minus 1 plus 1 is equal to a power 2 power n plus 1 plus a power 2 power n plus 1. You can check it out just by doing the same set of identities and multiplying. You can cancel many of the factors. All the negative ones will remain, all the positive ones here got cancelled with the previous one, right?
Yeah.
Do you understand what I'm saying?
Yes, I understand.
So that just shows us right now that a square plus a plus 1 is one of the factors of this.
Right.
Because ultimately you are ending up with one term like this and so many negative style terms, but only one term here, a square plus a plus 1,
Yeah.
right?
Right.
Basically, that finishes the proof. The point is that we are using the product of a plus b into a minus b identity to get a lot of identities like this.
Yeah.
And you can prove that this number is clearly divisible by a square plus a plus 1, right?
Right.
Another way to do the same proof, if you don't want to use these identities, you have to use induction to prove. Induction proof, you will have to do the base case. We already saw that in the base case, they are same. And
Yes.
then you will have to assume that it is true for n, that a square plus a plus 1 divides this. And then from there, you have to prove that it will be true for n plus 1, right?
Right.
So I didn't want to show the induction proof because usually you don't use induction right now, but that is a valid way to prove it also, right?
Right.
Similarly, like you can generalize the identity, the same identity, you can generalize a little bit and also say things like a square plus ab plus b square multiplied by a square minus ab plus b square multiplied by a power 4 minus a square b square plus b power 4 and so on till a power 2 power n minus a power 2 power n minus 1 b power 2 power n minus 1 plus b power 2 power n is going to be equal to a power 2 power n plus 1 plus a power 2 power n b power 2 power n plus b power 2 power n plus 1. It's the literally same identity except I have a b also now, not just a square plus a plus 1.
Yeah.
The way to prove it is the same as before. You start off by saying a square plus ab plus b square multiplied by a square minus ab plus b square. That will give you the first identity, which is a power 4 plus a square b square plus b power 4, right?
Yeah.
Now replace the terms a with a square and b with b square. You write another identity here, right?
Uh-huh.
Do you understand what I'm saying?
Yes.
Keep replacing a with a square, a power 4, b power 4, a power 8, and b with b square, b power 4, b power 8, and so on. And you keep getting sequences of identities like this. At the end, you have to do product of all of them and cancel the stuff. Like cancel this term with this term, it will get cancelled.
Yeah.
And this term with the previous term and so on. And you will be left with this identity.
Right.
Again, this identity tells us that the first term a square plus ab plus b square divides this in general. Do you understand what I'm saying?
Yes.
So it will help you prove some divisibilities which might not be otherwise obvious. In the same way, you can also prove that for integers a and b, and 1 is less than j less than equal to n minus 1, then there is an identity like this also: a minus b into a plus b into a square plus b square, and so on till a power 2 power n plus b power 2 power n is equal to a power 2 power n plus 1 minus b power 2 power n plus 1. This is obvious, right? How it becomes combines and all.
Yes.
This becomes a square minus b square. That combines with this becomes a power 4 minus b power 4, which will combine with the next term, which is a power 4 plus b power 4.
Yeah.
And so on. This finally you'll end up with this. So this means that a minus b divides a power 2 power n plus 1 minus b power 2 power n plus 1. Right?
Right.
Again, that can help you prove some divisibilities in situations.
Yes.
So in general, these algebraic identities are pretty useful in proving divisibility problems, and you should be comfortable with using them. Okay.
Okay.
The next question is this: prove that for any integer n, 120 divides n power 5 minus 5 n cube plus 4n. Or seventh one, are you getting something?
Oh, well, the prime factorization of 120 is 2 to the power 3 times 5, so it's like 8 times 3 times 5. And then you can take like n common from the equation to get n times n4 minus 5n squared plus 4. And then from that, from the 5n squared plus 4, you can like some the n4 minus 5n squared plus 4, you can like simplify that to like n squared minus 1 and then n squared minus 4.
Mhm.
And then you can expand those to get like n times n minus 1 times n plus 1 and times n minus 2 times n plus 2.
Okay, so basically we have this expression n power 5 minus 5n cube plus
Yeah.
4n can be written as n minus 2, n minus 1, n, n plus 1, n plus 2.
Yes.
Okay,
And then because they're consecutive, you know you have a 2.
you know
So
much more
because
than that.
because there's like 3, so n minus 2 times n minus 1 are consecutive, so that's a 2. And then n times n plus 1, that's also a 2. And then I guess you could take another one in between to get 3 2s for the 8. And then because there's 3 consecutive numbers, like you can take any 3 consecutive numbers out of this, you get that divisibility by 3. And then because there's 5 in total, you get that divisibility by 5.
It's not super convincing right now. You have to give me a better reason. 8, I did not understand. How did you get 8?
Uh, 8 is where I'm iffy about, but could you say like you could break it up into pairs, so like n minus 2 times n minus 1, you know that's going to be divisible by 2 because they're consecutive. And then n minus 1 times n, you know that's divisible by 2 because it's consecutive. And then so on to get like 2s.
But what if both the times you are getting because of only one even number n minus 1? You can't say 4 has come. Do you understand what I'm
Oh,
saying?
right. Yeah, I understand. Mm,
It's easy only as long as you think about these are 5 consecutive numbers, right?
yeah.
You can start with even, odd, even, odd, even, or you can do odd, even, odd, even, odd, right?
Yes.
Now, suppose in this case it is obvious there are 3 evens,
Yes.
so there is no need to worry about the case there. The only thing that we need to think about is if this is odd, starts with an odd number, right?
Yes.
In that case, is it divisible by 8? That's what you have to think of.
Mm,
So basically, let's take that case. Let's say n minus, here n is coming as odd, right?
yeah.
Okay, so n is coming as odd. And in that case, notice that you have product of two even numbers. If n is odd, n can be written as 2k plus 1, right?
Yeah.
What is n minus 1? N minus 1 would be 2k, and n plus 1 would be what?
2k plus 2.
And then when you multiply these two even numbers, what are we getting? 4 times k plus 1,
Yeah.
which automatically has another even number hidden inside it. Because k into k plus 1 is product of two consecutive numbers. One of them has to
Right.
be even.
Correct. Yeah.
So basically it is divisible by 8 again. 8 divides n square minus 1. We had already proved that earlier also.
Right. Yes.
If n is odd, 8 divides n square minus 1, right?
Yes.
And here you have n minus 1 and n plus 1, and n is odd in the second case.
Right.
So it is already done that both the cases you have divisibility by 8. In the
Right.
first case, you have that because there are three even numbers, obviously.
Yes.
In the second case, also there is divisibility by 8, even though from the outset it looks like there are only two even numbers. But the two even numbers are such that 2k and 2k plus 2, it automatically is divisible by 8, right?
Right.
Do you understand what I'm saying?
Yes, I understand.
We have done divisibility by 8. We need to do the rest of the thing. 3. What about 3?
So for 3, because there's like 3 consecutive integers, you can just say at least one of them's divisible by 3.
And for 5?
There's 5 consecutive integers, so at least one has to be divisible by 5.
So all of that is obvious,
Yeah.
right? So the whole thing will be divisible by the product of 8 and 3 and 5, which is 120, right?
Yes.
Okay. Write down this question. This is something you need to try and prove.
Okay.
And I will give you some more questions after that. Just write it down first.
Yeah.
Okay. That has to be tried at home. The next one is question 9. Let n be an integer prove that n squared times n plus 1 minus 1 divides n times n power 4 plus 1 minus 1. Okay, so last question is A and B are non-negative integers. You have to prove that A factorial B factorial divides A plus B whole factorial.
Yeah.
All of these questions are not very difficult. If you try it a little bit, you should be able to do almost all of them. Okay.
Okay.
So
Yeah.
from question number 8, which was on the previous page, from there onwards till 13, try these out. Thursday's class will also be number theory. So this is due by Thursday. So try
Yes.
this out till Thursday's class. Like we will just work on it. It will be done. And most of them are quite easy. You should be getting it.
Right.
So
Yeah.
we'll continue with number theory only on Thursday, and we might look at some AMC 10, 12 questions also on Thursday.
Yep.
Okay, that's all for now then.
Okay, bye.
Bye.
Thank you.
Hmm.